in this lecture we continue our discussion on the concept of equilibrium in classical mechanics. So, in the last discussion we were talking about the general concept of equilibrium, and we showed that, I mean, we introduced the concept that the equilibrium is a state of compromised unperturbation. That means compromised state where you have several efforts for perturbing the state of motion, but somehow since they are balancing each other for some points in space during its motion, then for that point or for those points, I would say like some points, sometimes it can be more than one points, but not all the points. If at all the points it has zero force acting on this, then it is exactly, I mean, identical to a force free situation. But here the equilibrium is very much interesting in the framework of classical mechanics, when at some special point in the field of movement of the particle, the situation arises where the vector sum of all the forces becomes 0, and that is why at those points, especially the system actually it experiences a special condition just like a force free particle, okay, and this is called the state of equilibrium. We will actually now will try to introduce you somehow this situation with a very concrete example of that of a raindrop. So, you will see that when a raindrop comes from sky and somehow at some height it get condensed to become water drop, I mean the initial size is actually very small, and although we know from our knowledge that raindrops actually they gain masses as they are falling, but I mean I can just, for the sake of simplicity, I can think of a situation where the mass is not that much changed. So, the assumption is raindrops mass is fixed, and another point is that it is actually falling exactly under the effect of two forces. One is the gravity, which is pulling it downwards and vertically downwards. So, I can think of, so you see like the phenomena is actually very close to the earth's surface, and that is why you can just think of a just like this as a plane, and a raindrop is just moving like this, and you can think that is just a vertical straight line which is directed downwards. So, you can think this is your z cap direction, which is in the downward direction. That is exactly what I presented over here, and then you can think that it starts from some 0 velocity, and after some time it has an arbitrary velocity Vz, and this is the velocity which is actually changing, and it can have actually some velocity in the other direction that we are now for this problem we are neglecting, and we are simply thinking that it has just a velocity acceleration in this direction. Now, as I said that it has more than one, actually two forces in action for its motion. One is this acceleration due to gravity, and so the force will be actually, so mass of the particle, mass of the raindrop times g, and another assumption here is that the raindrop at this point has so small size that it can be treated as a particle. So, raindrop is a point particle, okay, and that is why we are discussing this problem in this course. Okay. So, first of all it is actually moving downwards with acceleration which is mg, and here I am just writing scalar g because we know that the direction is j cap direction, I mean z cap direction, and then another force which is actually affecting the motion of this raindrop is the viscous drag. So, viscous drag of air. Now, what is the source of this viscous drag of air? That is beyond the scope of this course, but we are just thinking that since air is a continuous medium, it always can have effect on the motion of some particle. Now, you see there are some contradiction between this viscous drag of air and the assumption that the raindrop is a point particle, because if it is a point particle then it does not have a size. But on the other hand, viscous drag actually comes into play only when particle is of finite size, because you will see that whenever let us say you have some fluid, let us say air, and a ball is moving like this, then actually viscous drag comes into play due to this, principally due to this surface of contact between the ball and the fluid. If the surface of contact is negligibly small, 0, then there is the viscosity is also very less. Okay? That you can actually think that whenever you have a very small particle which you just which you just leave like this, and this particle easily falls down, but if you have let us say a sheet of paper, it does not fall down very easily or very quickly, actually it flies, because you see that due to its area of contact, large area of contact with the air, the viscous drag which is acting on this is larger. Okay? Now, for the simplicity, for the sake of simplicity, we just think that okay, it has some area of contact, but somehow this is for our case still can be thought to be a particle. And actually I will cover a little bit of system of particles at some time, and you will understand whenever you have a motion, let us say the raindrop has some finite size, and it is since it is consisting of many particles, actually infinitely many particles, but all of them are in this particular motion, all of them are actually performing or undergoing identical motion. Actually this whole system can be replaced by a single representative particle, which is called the center of mass of that particle. That I will come later, but just to tell you that apparently there is no severe inconsistency in those assumptions. That is what I was trying to say. So, now you have a point particle, point raindrop, where it is actually moving under G, it is experiencing viscous drag. For the sake of simplicity, once again I can model the simplest model of viscosity, air drag, which can be given me something like this, something proportional to Vz, and that I take the proportionality constant to be alpha. So, alpha Vz, and now if you write the equation of dynamics for this particle just along z direction, it will simply be m d2z dt2, which will be equal to mg minus alpha Vz. Okay. Now, you see here this thing in general is very interesting, because you can always think of a situation where this is 0, but none of them are individually 0. Okay. But somehow you see that when they are exactly balancing each other, you have a force, you have a net acceleration which is 0. Okay. But again what is the potential, what is the total mechanical energies of this particle? So, I can also write this equivalently as m dVz dt is equal to mg, and I can actually write this as alpha Vz, and then I can write m Vz times dVz dt, and I can actually write this as mg. So, there will be a Vz. So, I am multiplying everything by Vz, both cases. So, there will be Vz dVz dt, Vz minus alpha Vz square, and again although this is easy, but this is still interesting. So, ddt of m Vz square by 2 plus mg z, because you see Vz is also dz dt, that you cannot forget here. Okay. And this will come like this, and you can actually think this thing to be So, actually this is there will be a minus sign here, I am sorry for this, there will be a minus sign here, yes, and you will see that this will be exactly equal to minus alpha Vz square, which is of course less than 0. Now, because z is actually taken downwards, so minus z is actually positive in our case. So, this is nothing but the total mechanical energy. Now, ddt of this is less than 0. So, the energy is not conserved, energy is not conserved. Okay. Also, although you can have a situation where these two balance each other to have a 0 acceleration. Now, when they will balance each other, I mean this is also very easy to understand. When you have mg is equal to alpha Vz or Vz is equal to mg by alpha. At this point you see what happens, that this one balances this one and this has 0 acceleration. Now, this is not the end of the story. What is the observation? The observation is very important. Once you have this velocity, then at that instant or at that point of time or point of space as well, because you see here time and space, they are actually monotonically related with each other. So, you see that once Vz has this value, then at some height z from the initial point it has, and with this Vz. So, when this height is, let us say I would call that z star and Vz star, okay. I can call that Vz star actually, okay. If there the values of the position and the velocity of the particle, then suddenly it has 0 acceleration. Once this has 0 acceleration, what happens? That you see that this one is a constant force. Now, since at this point it has 0 acceleration, which is exactly equal to this, and it has 0, so you see that Vz and after this point will not change. If Vz will not change, because dVz dt is 0, then this drag force will also not change, and this is a constant force. So, if at this point at z star and Vz star this one start balancing this one, the balance will be remaining true or valid during the rest of its motion. So, once again, once the Vz has a specific value which is exactly equal to mg by alpha, then this part is 0 and then Vz cannot increase or decrease any longer. And then what happens, that this alpha Vz is fixed in this value. Now, what is this special value? So, alpha Vz is fixed at alpha Vz star value. Now, why this value is special? Because at this value this is exactly equal to, in magnitude is equal to mg. Okay, and they are actually vectorially equal and opposite, this one and this one, and they are balancing each other. Once they are equal and opposite, and since after this point this will not increase or decrease anymore, the balance will be locked. So, this will be a locked situation. So, for the rest of the motion of the particle will always fall with this velocity Vz star, and this is known as, so I just write over here with a different ink, terminal velocity. Now, what is the interesting point about terminal velocity? If the terminal velocity was not there, then actually what happened? The particles, the raindrops which were coming from very far, they could always, I mean, continue accelerating, and finally the velocity and the momentum with which they would hurt us would be much greater, and we could have some effect. Now, you see, due to this terminal velocity, after some distance covered, the velocity is limited to some terminal velocity, and that is why when we receive the raindrops, they are not that much hurting, okay? They are not that dangerous. Okay? On the other hand, at this point I would like to mention there is another very interesting effect, the effect of the changing mass of the raindrop, that we have neglected here just to tell you the equilibrium. But if you have a raindrop which is actually physically much more reasonable, which is gaining mass, so due to that gaining mass, if you do properly use Newton's law, you will see that in gaining mass basically actually tries to reduce the velocity of a particle. Okay. So, and in that sense, that gaining mass also can try to act like a dissipative or drag force. Now, you see that if you have one conservative force field and two dissipative force fields, so when the equilibrium is reached, then the equilibrium will be a little bit different. That is, that will be a balance between the conservative field, that is the acceleration due to gravity or the force due to gravity, and the air drag force, and also another drag type of force due to the change of mass. If you make the vector sum of all these three things to be equal to 0, then only your dV/dt, you can think of a system where your, situation where your dV/dt may reach some may reach 0, and your velocity and the velocity of the raindrop actually reaches the terminal velocity. And actually it is sometimes seen that actually the terminal velocity, which you can calculate by just this simplistic formula, is a little bit greater than what actually it is also received practically. And one possibility is, and one reasonable possibility is that that is due to, because the raindrops are also gaining mass with time. Okay. So, this is, and of course, the realistic situation is different. It has different shapes, and it is not spherical. Sometimes it cannot be just represented as a single point. Sometimes many raindrops can coalesce and make a larger shape, which no longer become symmetric, just that I was just telling. So, many things will be there. Then also air can have some other type of effect, air can move. So, all these possibilities are there. Here we are just thinking that the particle is moving, and air can also, air do not have that much of movement. Okay. But if air is moving in just this direction, in the horizontal direction, there is no effect, but if it is moving in the z direction, upward or downward, somehow locally if you have some movement, then actually one can take care of, in the simplest case, if the air is moving roughly at constant speed, then you can actually do this whole analysis like this, but then you have to just take a origin shift. That means you have to now work with the relative velocity of the raindrop with respect to the air. Those things you have to take into account. Okay. So, you see, this was a very important concept to impart. Now, I am coming to this concept of equilibrium and potential. Okay. So, as I said that at the very end of the last lecture, that whenever you in one dimension, so I just write in 1D. Okay. If you have u is the potential, so of course at equilibrium we expect, so equilibrium point is the x is equal to x0 point, and we will expect is this equal to 0 and d2u dx2 greater than 0 or d2u dx2 less than 0, but of course always evaluated at that point. That is very important. We said this is stable equilibrium, this is unstable equilibrium. Today we will try to understand why they are called so. Okay. So, for that what we will do, we will first take again the Newton's law. So, what is Newton's law? Newton's law is m d2x dt2 is equal to minus du dx. Okay. Now, at x is equal to x0, at x is equal to x0, m d2x dt2 at x is equal to x0 is 0, because as du dx at x is equal to x0 is 0, that we know. Now, if I perturb the particle a little bit, displaced a little bit by a small push, okay, so that I am not giving giving considerable amount of energy, so that the particle is perturbing much. That means the particle does not have any finite displacement, it is only infinitesimally small displacement. So that is very important here for the analysis. I perturb the system from x0 to x0 plus delta. So delta is my new variable, although small, this is the function of t, and that is why you still have a meaning for dx dt and dx d2x dt2, which will be actually, so if I do that, then actually your dx dt, so this is a constant point, you know, fixed point, okay. This is a point which you already know, known a priori. So dx dt will simply be d delta dt, and that delta is something you can change, but it should always be small, okay, that is something very important. So the assumption is delta should be very, very small with respect to x0 at least, okay. This is not, maybe I should not say it is x0, but because x0 can actually be thought to be 0 as well. So this is not a reasonable approximation, sorry for that. So delta should be in general a very small quantity, okay, which is somehow, what is the meaning of this small quantity? That means I can apply, so delta is small enough so that I can perform a Taylor expansion with it, okay. That is exactly the requirement. Now if you do that, basically what you will find that, okay, here I have just made this for another formula, I can do here, no problem. If you will make this, you will actually see that your u, which is now u of x and which is nothing but u of x0 plus delta, will be equal to u of x0 plus du dx evaluated at x is equal to x0 times delta plus half d2u dx2 evaluated at x is equal to 0 times delta square plus some higher order terms. Now delta is so small that we will not go above the second order terms, okay. Now this one is something which is a constant, this is the value of u at x0. Now you can simply say that this constant I can always choose, I can always choose to be 0, so that my u of interest will be actually not u exactly, but u minus some constant. I can call this as u0, okay. Then that is not a problem. Then I can make that u0 to be 0, or I can say that u minus u0 will be my u, okay. In both cases the analysis does not get affected, and you will actually see that your ux, so what you see, your ux will be equal to these two terms. Now again at x is equal to x0, by the definition of equilibrium, this term vanishes because this term vanishes, okay. And if this term vanishes at x is equal to x0, then the only term which is meaningfully surviving is this term. So that will be equal to then half d2u dx2 delta square. Now you see, if we say that this is evaluated of course at x0, if we call that this thing, if we call this thing to be k, okay, and we say that k greater than 0 and k can be also less than 0, then we will actually check that these things are nothing but these conditions. So in a sense we are saying that when k is greater than 0, then I have stable equilibrium, and when k is less than 0 I have unstable equilibrium, okay. But the original question remains the same, why should I say that? For that I will just take a place over here and I will make some small calculations, okay. You will easily see that. So what happens when your ux is actually half k delta square, Okay. I have just written this sign because we have neglected the higher order terms. Then your f x is actually minus delta, because now f x is nothing but, so f x is nothing but minus du d delta, because delta is the only variable part in x, x0 is not meaningful here, x0 is just a constant. And then the Newton's law said, Newton's second law says that what will be the equation of dynamics for the particle? It will be m delta double dot or d2 delta plus dt2, sometimes as I said dots are for ddt, okay, plus k delta is equal to 0. So, you see because this is nothing but f x and or f delta, which is nothing but minus k delta. So, this plus k delta will be 0. Now, if k is greater than 0, we know the solution is oscillatory. So, that means that if k is greater than 0, if you perturb the particle a little bit with respect to its original point or position of equilibrium, then the particle will simply perform a simple harmonic oscillation, okay. And that is how a position of stable equilibrium is defined. On the other hand, if k is less than 0, then the solution will be solution of m delta double dot plus k delta will be is equal to 0, will be some delta is equal to some a e to the power some constant which is the root over minus k by m actually will be there, then t plus b e to the power minus root over k by m t, okay. So, this is either your displacement after some perturbation, small perturbation, either your displacement is exponentially increasing with time or it is exponentially decreasing with time. So, in both cases we are talking of unstable equilibrium. So, you see, if the equilibrium position is such that a small perturbation on that equilibrium position would lead the particle to perform simple harmonic oscillation with respect to the equilibrium point, then we call that stable equilibrium position, okay. So, this is the case, stable equilibrium. If the particle either goes directly to kill its displacement and very fast like this, or it increases very fast its displacement from the equilibrium point, in both cases we talk about unstable equilibrium, okay. Now, you will see that in most in natural systems, most of the times we say that for a stable equilibrium system, if you just perturb the particle, then the particle will actually come back to its initial position. That is not the correct interpretation. The particle, if you perturb with some energy, then the particle will actually, in an ideal case where there is no viscous or drag effects or dissipative effects, the particle will forever perform as a simple harmonic oscillation. The particles most of the time they actually come back to the initial position after some oscillatory motion with decreasing amplitude, that is because of the natural viscous forces, okay. So, before ending this lecture I am just going to discuss a little bit this problem, that is somehow an easy problem and you will actually check this thing. So, what is the type of motion or what is the this equilibrium, points of equilibrium and the nature of equilibrium when a particle is just moving under this potential u x is equal to x square by 2 minus x to the 4 by 4. Now, you see here there is a potential function, so which I can write y is equal to u of x. So, that is the potential function and here I plot this as a function of x. So, when x has very small values, then this term is negligible with respect to this term dominates and you have a parabola. So, that is why points which are close to 0 and not the large points, you have something like a parabola over here, y u is equal to x square by 2. When the large values are coming for a large values of x in both negative and positive and negative sense, you will see that you will have something like these things will be somehow start dominating, and at some point it will actually balance this thing so that ux becomes 0, and then finally it makes the whole ux, then it dominates largely in such a manner that finally you will see that ux becomes will tend to minus infinity in both the cases when x is increasing towards positive infinity, or this is the case, or x is tending towards negative infinity. In both the cases you will see that u will be actually tending polynomially, in the power of 4, okay, to this negative infinity. Now, you will also see due to this type of potential curve, we have 3 possible regions, 3 possible points actually, not regions, but 3 possible points which can act as a maxima or minima. We can actually confirm that just by doing this small calculation. So, du dx is equal to x minus x cube, and we know for equilibrium du dx should be 0. So, we know this equation has 3 roots. Okay. One is x is equal to 0, another is, so because okay, I can just write x 1 minus x square is equal to 0. So, either x is equal to 0 or x is equal to plus minus 1. Okay. So, at those 3 points it will have some maximum or minimum. Okay. So, if you just now calculate d2x dx2, sorry, d2u dx2, then it will be again 1 minus 3x square. Now, this will be somehow, I just use this in, yeah, this will be somehow equal to 1 at x is equal to 0, because as x is equal to 0, this is 1. Okay. At x is equal to plus minus 1, in both cases you will see that this will be minus 2. So, minus 2 at x is equal to plus minus 1. So, we can actually cross check that really at x is equal to 0, this has a minimum, and at x is equal to plus minus 1. So, we now know this is minus 1 point and this is the plus 1 point, it has 2 maximum. Okay. Now, you see that we can easily now think that okay, so these are the points of equilibrium, and this is the stable equilibrium point, and this is the unstable equilibrium point, the same for this unstable equilibrium point. And now, you will actually think of another point, that is what will be the value of u at those points, and are they really the the minimum or maximum, that is another step further, but just at least to understand what will be u. Okay. So, if I just say that what will be u, so u of x for x is equal to 0 will be 0. So, you see here, that is the point. So, u will be exactly equal to 0 here. Okay. So, at how to say, at x is equal to 0. Now, at x is equal to 1 or minus 1, because this is an even function, this will be symmetric. Okay. So, ux at x is equal to plus minus 1, you will have actually so half minus 1 by 4, which is 1 by 4, which is nothing but 0.25. So, these will be actually in this thing 0.25. Now, you see the only point I was trying to say, you know that ux, the minimum value of ux is actually minus infinity over here, but I am deriving here that this one is the minimum. okay, and this is 0. But I mean, is this contradictory? The answer is no. We are just defining the points of stable equilibria to be those points which are local minima. Okay. You see that in this locality, when you have two maximum values and these two are actually separated by a minimum. So, in this local region, okay, or even in this locality, or you can say that okay, I can take even this domain from this to this, okay, where I mean in this domain I can see that there is one point which is really the minimum point, and this is minimum. This cannot be minimum because after that it is also decreasing, but here you see this is the minimum point because just before and after this the u function increases. Okay. So, that is why this is the local minimum, and a point of equilibrium is stable equilibrium if the point is just a local minimum. It can be a global minimum as well, but this is not necessary. Okay. On the other hand, for this unstable equilibrium as well, it should be actually either local I mean it should be just either local maximum or global maximum, but at least local minimum will be sufficient. Okay. If there is no other minimum, then global and local they are the same thing. Okay. Thank you very much.